I talk about MEF2C, a transcription factor that forms a dimer that's best represented via the Swiss model that was threaded against a homolog, because it's a dimer that binds to DNA, whereas the AlphaFold model, as we saw, was no good. Here I'd like to talk about a different protein, LZTR1, because this protein binds to HRAS, and the problem is that there is no crystal structure of LZTR1 bound to HRAS. As a result, we do need to get a bit creative. So, in Pagnmenta et al., there's a list of variants, so let's copy these. And now, Venus only analyzes one mutation at a time. So if we click on the multiple mutant page, we can get an overview of where these mutations may be. Hopefully there's no "and" over that. No, there wasn't. Fantastic. So over here we've seen that there is a model has been generated from AlphaFold, and we can see that the various residues seem to cluster over here. This is a known feature, except for this chap over here, arginine 97. Okay, let's have a gander at arginine 97. We want to see where this residue falls in the context of where HRAS is located. As there's no model of the dimer in the PDB or any homolog, we have to make it ourselves. If we press Analyze, which is the location where one can choose what's controlled by what, we can upload our own model. So AlphaFold does only monomers, but there is a modification of AlphaFold called CollabFold by Sergei Ovchinnikov and his lab and collaborators, which allows one to calculate complexes. So let's say we've run that before. Let's upload the file that we've got, and now let's see what we get. Let's use this guy, and now let's analyze. So now it's doing the various analyses as before, but we should see soon, once it finishes tweaking the model, we see a dimer, which we do see. As expected, whereas all the other mutations fell over here, this mutation here falls on the side, which means that this mutation is not at the interface with the other variants. So let's see this neighborhood. It's the calculations for the delta delta G of the neighborhood are finished, so we can see what we've got. So our target mutation, the arginine 97C, is predicted to be neutral at about 1 kilocal per mole, which is within error, basically. We can see that there actually is in the Nomad database of wild-type mutations in the healthy population, we see that there's an arginine 97 heterozygous mutation. And this is humongously destabilizing. The computer didn't finish to calculate what the effect is. It just basically gave up because it's a huge value. But this is a truncation, so obviously no delta delta G could be calculated. This substitution is also highly destabilizing. Another truncation, destabilizing, another truncation. So what we can say is that the neighborhood of this residue is affected by several destabilizing truncations, which is consistent with the fact that that truncations and destabilizations do not cause the de novo phenotype seen in arginine 97 cysteine, because this dominant phenotype is neutral for all the various mutations, or near neutral, whereas a homozygous case of a truncation or a destabilizing substitution results in a completely different phenotype. So, so now that we've seen that, we can see that everything's destabilized. Previously I clicked on phosphorylated, so let's have a gander of where these phosphorylations lie. As mentioned before, a lot of these phosphorylations are over here, which is cool. We've even got over here a phosphorylation that seems to be involved with the other, with the complex with HRAS. So that's cool. So that, but over here where we had our mutation are some phosphorylation sites. So probably something else is going on over here, where this neutral in terms of stability mutation may be having a role. Hence why, I mean, whatever these phosphorylations are doing, this may be tinkering or tampering with it.